Talking about a problem that had a very interesting twist. Took me a few minutes to figure it out. You were long gone.
Yeah.
The problem we were working on was this one, right there. And it's very interesting. Let's just sort of talk about the geometry of it for a minute, and then we'll talk about why the approach I thought would work didn't work, and the approach that we have to use. So first off, the idea is that we have a paraboloid, so an upward opening paraboloid, and we have a curve down in the xy plane, or we have a disk. We have a circle of radius 4, and we're looking at all the points on the inside of it. And we're looking at that boundary curve, x squared plus y squared equals 16. And so here is a graph from GeoGebra. You can see the paraboloid, and then the curve in the xy plane, I entered it as a cylinder, and you can see where the two intersect. And so the idea is that we've got this paraboloid, and then that circle in the xy plane, when it lifts up onto the curve, it creates like a roller coaster around the edge of the, at this intersection curve. It's kind of like a roller coaster. And we've got a high point here. We'll have a high point 180 degrees away. We'll have a low point here and a low point 180 degrees away. And so the math that we were coming up with wasn't making sense when we were looking at the boundary, and I couldn't figure out why aren't we getting critical points there and there. So remember that what we did was took our curve and we plugged into the function to create a function of one variable, which in general works, and we're going to do it a bunch today, and it will work. The reason it didn't work here is that we're trying to create a function of x. And when we're trying to create this function of x, we were plugging in y squared, but really what we're doing is plugging in, we're trying to create a function of x, and this circle is not a function of x. So if we think about plugging in the upper semicircle, y equals the positive square root of 16 minus x squared, x equals -4 and x equals +4 are boundary points for that curve. So those boundary points have to be tested separately. And what we saw was that if we if we turned it into a function of y, those two critical points would show up, but these two wouldn't. Same reason, if we wrote it as a function of y, down below at y equals -4 and up above at y equals 4, that semicircle is not a function of x, function of y. And so we have to test those 2 points separately as boundary points. So what we do end up with is what we kind of intuitively knew. We're going to have 4 points that we have to test. So the way we did it, we had to test those 2 because they are boundary points of this substitution. Now the easier way, which I don't know why I chose not to do it that way, but what I learned was a lesson, and that is whenever your boundary curve is a circle, whenever it's not a function, it's better to parameterize it. And there's only a few of these in the book, and so it just didn't occur to me that that might be a problem. So those 2 points are bad if we do that substitution. So that's what we were doing yesterday or last class. And so those are boundary points, so they have to be tested separately. So that means we have to test these guys separately, the whatever it was, pi/2 and 3pi/2. Those two had to be tested separately. But here's the easier way to do it. The easier way, where you don't have that weird extra hidden boundary point, those 2 extra hidden boundary points, the way that you can get away with it without having to think about hidden boundary points is to parameterize it like this, as a function of theta. Because when we parameterize as a function of theta, it doesn't matter about those hidden boundary points get absorbed. That is a function of theta. Yeah?
Yeah, just about your learning lesson. Yeah, programmers have a philosophy of the best programmers are the laziest ones. So I'm thinking that might apply to math too.
Yeah, we got to do it the easy way. And we learn lessons as we try things differently. So if we do the theta thing, it works out really well. So we go back to our original function, 2x squared plus y squared. parameterize a circle of radius 4, and that is now a function of one variable. When we simplify it, function of one variable, take its derivative, and we get this. So when is this equal to 0? When cosine is 0 or sine is 0, and that gives us our 4 points, our 4 quadrantal points. So those are our 4 critical points on the boundary. And so if we go back to here where I plugged them all in, oh, I guess it was the next page at the bottom or something. I feel like there's more pages here than there are supposed to be. Where the heck? Is there stuff at the bottom of that? Where is it? Oh, right there. There it is. So those 4 theta values correspond to those 4 points. We test. The biggest number is the absolute max. The smallest number is the absolute min. So the moral of the story is if your boundary curve is a circle, parameterize it according to theta. Because if you do a y equals thing, then you have 2 hidden boundary points. If you do an x equals thing, you have 2 boundary points that are hidden. So if it's a circle, parameterize it. So let's do this one, number 46. So 46, similar type of thing. We have a function, a surface, and it's defined on a closed and bounded region. But notice that this one's different. Our boundary is 4 separate straight lines. So we're not going to have to deal with what we just dealt with, and we'll see that you can just turn your original function into a function of one variable. All right, so let's draw a picture of our region in the xy plane. X goes -2 to 2, y goes -1 to 1, so we've got this rectangle. Let's see, y -1 to 1, x -2 to 2, so something like that. And the boundary is included. So this point over here is 2, 1, that one's 2, -1, etc. So first, we're going to look on the inside. The inside, so the interior points here, not the boundary, we can use the second partials test. That's what the second partials test is all about, is for the interior of a domain. So to use the second partials test, we figure out all these partial derivatives. F sub x is -2x. F sub y is -8y. And then we have to find critical points, if any. To find the critical points, we set each of these equal to 0. And we end up with one x value and one y value. So there's one ordered pair that is a critical point. So therefore, the 2-variable critical point, there's only one 2-variable critical point, and that's at the origin. So this is a 2-variable critical point right there. Let's test and see what it is. If it's min, because there's only one, it would have to be an absolute min. If it's a max, then it would have to be an absolute max, because the function's not turning around inside that rectangular area. So let's check. So you might already know what's going to happen up here if you are good with the geometry. This is a paraboloid that opens in which direction? Down. It opens down because both the x squared term and the y squared term are negative. So we kind of know that we should be getting a max. So let's test. So we need our second partials. So f sub x, the partial of f sub x with respect to x. We need f sub y, y, the partial of f sub y with respect to y. And we need our mixed partial, f sub xy, which is the same as f sub yx, which is 0. So now we're going to figure out the discriminant at this ordered pair, this critical point, 0, 0. So those are our second order partials. Let's see, so we do fxx multiplied by fyy, subtract off fxy quantity squared. We get a positive 16. So that is greater than 0. Therefore, we have a min, right? We have a relative min. So the second partials test, if we have a positive number there, that means that we are dealing with a wait, what?
Didn't you say it should be a max?
Yeah, why is it a max? Who said min? Was it you?
You.
I said it. I thought you said it.
I said max.
Did you say max? I thought you said min.
I was so confused.
Yeah, I was so confused when I looked up at the board and saw the word min. Hung, you wrote that. So relative max. Why? Because we look at the second partials. Those are negative, which means concavity is down, which means we're talking about a local or relative max, because the concavity is down. When f sub xx is negative and f sub yy is negative, that means we have concave down. So we have a relative max. And psych! And that tells us that we have an absolute max because there are no other critical points in our region. There are no other critical points in the whole xy plane, in fact. Okay, so that tells us that we have an absolute max right there. Now we have to test the boundary. We know there has to be an absolute min because we have a closed boundary. Anytime we have a closed boundary, we have an absolute max and an absolute min for sure. All right, that's the extreme value theorem, and our two-dimensional picture is this. If we have it, if it's defined on a closed curve, a closed interval, there has to be an absolute max, there has to be an absolute min, and it could be the case that one of them occurs at the boundary, like this picture. Here are the absolute maxes at the boundary point. Here are the absolute maxes on the inside. But if it's a closed, bounded domain, there has to be an absolute max, there has to be an absolute min. And so now we have to test the boundaries. So our boundaries, we have 4 boundary curves. Let's see, I wanted to write, probably should not write boundary with an apostrophe S. Boundaries. So the boundaries, we have 4 curves. So we have x equals 2. Let's just go counterclockwise. We have y equals 1. We have x equals negative 2. And we have y equals negative 1. Those are our 4 boundary curves. So when x is equal to 2, what we are going to do is take a look back up at our function, x is equal to 2, and we're going to plug in x equals 2. On this curve right here, x is always 2. So we're going to plug that in up here, and our function value will be dictated totally by the y-coordinate. So when x is 2, we end up with 2 minus 4y squared. One variable function, we can differentiate it. But remember, this also has its own boundary points. Right? These two points right here are boundary points for that function. So we're defining that function of y. That function of y going from -1 to +1 is just measuring critical points, one variable critical points, on the inside of that interval. We then have to test those boundary points separately. Here it's more obvious. They're not hidden inside of a circle. Totally obvious. We can see them. And so we'll have to test those 2 points separately. Then we go to y equals 1. Y equals 1. Back up to the function. Plug in y equals 1. 6 minus 4 is 2, so we have 2 minus x squared. So we get f of x equals 2 minus x squared, one variable function. Its derivative will find one variable critical points interior to this line segment right here, y equals 1. Again, it's got 2 boundary points that have to be tested separately. Third function, x equals -2. Plug in x equals -2, we get 2 minus 4y squared. Same as we already had. F of y equals 2 minus 4y squared. Plug in y equals -1. It's going to be the same as y equals +1. So we're going to end up with another one variable function of x. We're going to get 2 minus x squared. So these are one variable functions. The derivatives set to 0 will give us one variable critical points. So let's go ahead and do that now. So f prime of y, negative 8y. And we then set that equal to 0. And that tells us that y is equal to 0. So we go back up to our picture. And we're looking along the line x equals 2. And we're trying to decide, is that critical point in the boundary? Like, it's possible that maybe y was 4. And then y would not be on this boundary, so we would exclude it. But y equals 0 on this curve is right there. So that is definitely a one variable critical point that's interior to our interval, so it has to be tested as a potential absolute max or absolute min. So we've got that one. Now we go to the next curve, y equals 1. So now we're on that top edge. Take the derivative, f prime of x, that's equal to negative 2x. We set that equal to 0. That tells us that x equals 0. So these guys over here are one variable critical points. One variable CPS. One variable critical points are right there. Y equals 0, so x equals 0. That right there, we're looking on this line segment where y is equal to 1. That point's interior to that segment, so then it counts as a one variable critical point. Down here, we end up with the same stuff for both of those. So we can use symmetry here. So we're going to get the same thing over here. We're going to get that y is equal to 0, which is going to be that as a critical point and that as a critical point. So we have three things happening here. We have three different things going on. Let's use three different colors. So this right here is a two variable critical point. We used the second partials test to determine that it was a relative max, which turns into an absolute max. These four red points, those are all one variable critical points. So one variable critical points, each of these four right there. So those are all one variable critical points. And then the four light blue, those are all boundary points. So we have three different things happening. Two variable critical points, one variable critical points, and boundary points. So now we have to test all that stuff. So come down here. Now we're going to test. So we set up a little table. We have our critical points. And then we have the value of the function. Value of the function. So our critical points, we had our two variable critical point right there. And we plug that into our function. I need to bring that function down just so that we have it closer. So let's copy it and bring it down. Right here. So we have it at our disposal. Paste. Oh, come on. Really? Paste.
I don't think you copied it.
Did I not copy it right? Down, copy. Copy? Did we copy that time?
I think so.
It might need, it might not be totally oriented. Okay, there we go. All right, so there's our function. And let's evaluate it at 0, 0. We already did that. Plug it in 0, 0. We get a function value of 6. We'll see that that's going to be the absolute max. We already know it's the absolute max because of our second partials test. And then we have to test our one variable critical point. So we are over at 2, 0. And then the next one was what? 0, 1. And then we had negative 2, 0. And then we had 0, negative 1. So these are the one variable critical points. One variable critical points. This one is our two variable critical point. And then we have our four boundary points, the four corners, the four vertices of our domain. So these are boundary points.
And it's the other way around? The four top were the boundary points and the
ones you're about to list are the critical points?
These are the critical points right here. 2, 0, 0, 1,
Yeah.
and negative 2, 0, and 0, negative 1. So the ones on the corners are going to be the boundary points. So let's get all those listed. So that's 2, 1, negative 2, 1, 2, negative 1, and negative 2, negative 1. All right, so those are all the points we have to test.
Oh boy.
Oh boy, this is so hard. Oh, I'm so sorry. Not. Plug in the x equals 0. Excuse me, x equals 2, y equals 0. We get 2. This isn't that hard. Plug in 0 for x, 1 for y. We get negative 2. Plug in negative 2 for x. We get 2.
Yeah, how'd you get the negative 2?
That negative 2. Let's see. I don't know. Plugging in 0 for x. Plugging in 1 for y, 6 minus 4. Oh, is that a positive 2?
Yeah.
Thank you. So positive 2's. And then plug in our boundary points. So 2 and 1. So what is that? 6 minus 4. Is that negative 2 there?
Yes.
Negative 2. And it's probably going to be the same for all of these, correct?
Yeah.
Because they're all squared. So those will all be negative 2's.
So we just have multiple absolute maxes?
Yep. I mean, we have one absolute max that occurs in multiple places.
Okay.
So if we look at a picture of it, it's kind of like the roller coaster thing that we had on that other problem. So it's reaching the absolute max at multiple places.
So if we were to get
Or
this,
absolute min at multiple places. The absolute max is only reached at one place.
that's what I meant. Absolutely.
Yeah, that's...
But if we were to do this on a test, let's say, and we only got one of the absolute mins, how much credit would we lose for a question? Okay. What would happen?
So if you got the absolute min correctly, but you didn't label all the places where it occurred,
Mhm.
I mean, you get most of the credit. You get most of the credit. If you get the correct absolute min, but you didn't label all the places where it occurs, you'd get most of it. Yeah.
You would be exiled, though.
You'd be, yeah. There'd definitely be a consequence that
My time
cannot
on the
define
island
at
is
this
done.
moment.
Should I take off my torch and everything?
there'd definitely be some humiliation. Okay, so let's take a look at this one. So with that last couple, we had a closed and bounded domain. And what we've seen is with a closed and bounded domain, the function has to have an absolute max and an absolute min. If we have a domain that is not closed, sorry, Cube. If we have a domain that's not closed, so if we have something like this, then it's totally different, right? Here we do have an absolute min, but we don't have an absolute max. So if we don't have a closed bounded domain, things are totally different. And that's what we're dealing with here. Yeah?
What if the domain is Clopin?
If it's Clopin? We're not talking about Clopin domains. It's way too complicated.
Thank God.
We'll stick with open or closed. Clopin domains. So find absolute max min values for this. So let's go ahead, let's draw a sketch of our domain. Oh, what a great word, right? Clopin.
I used to use when I was in the restaurant business. They had to close one night and then open the next day.
Oh, there's a Clopin night,
Open shift.
Clopin shift.
Oh.
Close at night, open in the
Really?
morning.
Yep.
Yeah. I told you it was a real word.
I told you.
It's a real word.
We never said it wasn't, we just gave the fact that it's a word.
Yeah, right. That it has mathematical meaning. Okay, so here's our picture. And the boundary is not included, so let's get some dashes on there so that we can...
Oh, well, that would have been nice to know before I drew it.
I told you it was open. It's a good thing you're using a pen.
Oh.
No, I'm not. It's a good thing I'm not.
I guess it's a good thing you're not using a pen.
Good job, Miss.
All right, so there's our situation. Okay, so again, let's go look interior to the rectangle first. Interior, we're talking about two variable critical points. And two variable critical points are found by looking at the first partials. So we're going to look at f sub x, we're going to look at f sub y. So are there any two variable critical points? Are there any ordered pairs where the partials are simultaneously 0? No. The 1 is never 0. Unless you take an abstract algebra class, then sometimes 1 is 0, but we won't talk about that now. No, we will not talk about that now.
Please, let's not get into 2 plus 2 does not equal 4.
Let's not get into modular arithmetic. Although, you need to get into modular arithmetic if you want to look at the Riemann hypothesis that 90-year-old man said he proved. But I don't think he did it.
Have you actually read it?
Not yet. Okay, so
Walk
and it's short. It's only short. It's only like 18 pages. It's not that
5
long.
pages.
Oh, it's 5
Yeah, I was
pages.
gonna say.
5 pages.
Even
It's not
shorter.
that long. That's very short. That can't be correct.
What's the average for like math stuff like that?
So I mean, a lot of those theorems, like the proof for Fermat's theorem, was hundreds of pages.
Oh, wow.
Also, is this more like the $1 million problems where if you solve it, you get $1 million?
Yeah.
Like,
It is
one of
there's no way
those.
this is. Yeah.
It is one of those. Yeah.
There's no way.
I mean, what's a 90-year-old guy going to do with $1 million?
He's gonna keep himself alive for another 90 years.
Good point.
And then once he's that old, he'll have had enough time to solve the next one.
Yeah.
It's usually people in their 30s and 40s that are solving these things.
I don't know, man. $1 million doesn't go as far as it used to.
That's true.
That's true. All right, so there are no 2 variable critical points. That means the absolute max and the absolute min have to occur somewhere on this boundary. So we have 4 boundary curves. We have to test those 4 boundary curves for 1 variable critical points. And then we have to test the boundaries of those 1 variable functions. So those 4 vertices that we see, those are boundary points for the 1 variable functions on each of the edges. So first one, let's go counterclockwise again. We'll start with x equals 1. So that's our first boundary curve. We plug that into our function, so that creates a function of just y. When we plug in x equals 1, we get 3y plus 1, or 1 plus 3y. Take its derivative, f prime of y will be 3. Does that have any 1 variable critical points? 1 variable critical points, none, because that's never 0. So that means there are no 1 variable critical points on this right edge. Then we test the next edge. What's that? Y equals 2. Y equals 2. Yes, y equals 2. That creates a 1 variable function. When y is 2, we get x plus 6. Take its derivative, and oh, you know what's funny here? I'll tell you in a second.
I think I
We wanna
know.
know.
Yeah, do you already know?
I don't think there are any critical points, are there?
We actually are already doing more work than we need to.
Because yeah, the boundary's open. So why? Are you
Because the boundary's open.
Yeah.
Right?
What's the point of that?
So the boundary, yeah, I'm already doing more work than we need to. So we're in a situation where there are no critical points on the inside. So that means we're in a situation like this. If we wanted to do a 2-dimensional analog, because we're not including the boundary, we're dealing with a situation kind of like this. Is there an absolute max or an absolute min there?
No.
No. So right away, we didn't actually have to go into the boundary thing. We already know because the boundary is not included because there's dots
So the
I was
only work
confused
you
as
had
to
to
why you
do
put
was
those.
the
On the
first
inside.
part? Okay.
So if the boundary is closed, if the boundary is bounded, but it's not, but it's open and not closed, then we don't have to test anything on the boundary because the boundary is not included.
So can we stop?
Right? We can stop. We did not have to. This is good practice if the boundary was included, but if the boundary is not included, right here we can say that there is no absolute max or min. So if the boundary is included, there must be an absolute max and min. If the boundary is included, but if the boundary is excluded, there does not have to be. So we could continue this on, though, to figure out, the secondary question, if we did include the boundary, where those maxes and mins would be. But for the question as stated, we could make our conclusion right there. Yeah.
So, so hold on, just something that occurred to me. So for that first graph you have, the absolute max, is that the little peak point there and not the part where it approaches B?
This here? So this one has no absolute max over here,
Okay.
but it does have an absolute min right down here.
All right. Yeah, just making that. Just wanted to make that.
Yeah, absolutely. And so over here we have no absolute max and no absolute min.
Right.
And this is the situation that we're dealing with now. And so what we're seeing here, let's just talk about if we were going to include the boundary, this pattern is going to continue. And so if there are no one variable critical points, where would the absolute max and min have to be if this was a closed domain? Where would they have to be? If we have no two variable
At
critical
the-
point, it'd
at
have
the
to be at one of the
values.
vertices. Right? So we would test the value at our vertices. So if we plugged in -1, 2, we would get 5. That would be the function value here. If that was included, we would have f equals 5. Here, where we plug in 1 and 2, we would have, what's that? 1 and 2 is 7. Function value of 7. Down here, if we plug in a 1 and a -2, we get -5. So if the boundary was in fact included, we would end up with our absolute max being 7 and our absolute min being -7, if the boundary was included. Because there's no one variable critical points and there's no two variable critical points, so it's the vertices that come into play. Only the vertices. All right, let's take a look at this guy. Same idea. Let's draw a sketch of the domain. Here we have the unit square as our domain. Well, yeah, I guess that's called the unit square. The radius of the square is 1.
The unit square.
Yeah, is that a unit square?
Unit triangle.
It
I
is
mean,
now.
a unit circle has a radius of 1. Does a unit square have a side length of 1 or a radius of 1?
No,
Side
it doesn't
length
have
of
a
that.
radius.
Yeah.
Side length.
Yeah, squares don't have radii?
No.
All right, I'm with you. I agree. Talking about the radius of a square just sounds weird.
Okay. Just gonna do this.
Okay.
Didn't Leonardo da Vinci do some stuff with that?
I don't know.
I think he did. Like that famous painting of like the guy with like the 8 arms or whatever is like his idea about like transforming a circle into a square or something.
Oh, now that is, yeah,
Oh,
trying to turn a square into a circle or, yeah, that's impossible, but that's, yeah.
Well, not if you're Leonardo da Vinci, obviously.
You can do it with a picture, but not in math.
Alright. Although actually, mine was, I think my 3D modeling program actually uses the term radius when talking about cubes and whatnot.
Does it?
Yeah.
Yeah.
Kinda weird.
Okay, so let's go ahead and analyze our region here. Again, we're excluding the boundary, so we don't really need to think about it. All we need to do is look on the inside for two variable critical points. And we figure out our f sub x, we figure out our f sub y, we set those equal to 0, and we have one place where x is 0, we have one place where y is 0. So we have one two variable critical point. So our two variable critical point, again, is the origin. So if it's a min, it will be an absolute min. If it's a max, it'll be an absolute max. If it's a saddle, we won't have an absolute max or min. And what is the graph of this function? Do you know?
No.
You don't know?
Absolutely.
What are the traces?
X squared equals y squared. Is one
What are the traces? So the trace here is a
Parabola.
upward parabola, trace there.
Downward.
Downward parabola, trace there.
It's gonna be a.
Intersecting lines.
That's
Hyperbolic
definitely a
parabola.
saddle.
So we're going to get the hyperbolic parabola, the saddle surface. Yep.
Ah, I'm learning.
Yep.
I'm
Yep.
learning.
So we have one critical point right there. It's our only critical
So
point.
we know it.
Yeah.
Okay.
So the discriminant, if we figure out our other stuff, our f sub x is 2, but we know what we should be getting. We should be getting a negative discriminant because we have a saddle surface. And that point on the saddle surface corresponds to a saddle point.
Oh, because one of them is negative and one of them is positive.
One is negative, one is positive, so we have a parabola going down, we have a parabola going up. That's just offset by 90 degrees, and so there's never going to be a max or a min. It's all, points are always above and below that point. So f sub xy is 0, both these are 0. Wait, what? Oh, I looked at the wrong place, I think. F sub x. Are we
I think
getting?
it's 0.
Yeah.
Yes.
That looks right?
It's 0.
So how are we getting the saddle point then?
Because you get -4.
But we don't get -4.
Well, 2 times -2 is -4.
Oh, that's where the negative comes from. I see it now. Yes, that's where it comes from.
Well.
Excellent. This is so hard. Yes. Excellent.
Had a long weekend.
Yes. Yeah, it's hard. I was camping this weekend. It's hard with this arm camping. I didn't sleep so well.
Did you have to take your recliner with you? So
I wish I had my recliner. Camping 38 degrees with bad shoulder. My kids slept well.
That's good.
They didn't have a bad shoulder.
Kids sleeping well usually translates to happy parents. Okay, so that means we have a saddle point, so there's no absolute max or min. No absolute extrema. So again, we're dealing with an open domain, so there's not a guarantee that there's an absolute max or min. If we included this, we would go through the same boundary process. We would let x equal +1, plug it in there, we'd get -y squared. Let's take the derivative of that, that's 2y, we get y equals 0. So that would be a one variable critical point where we'd end up with those 4 points being one variable critical points. And then we'd have to test the function value for all 8 points. The 4 one variable critical points and the 4 vertices. And then we pick the highest number is the absolute max, the lowest number is the absolute min. Oh, bye. Bye, section 8. See you later.
No, there's one more. There's one more.
Oh no.
Where is it?
You guys are crazy.
Is there one more?
This one.
Oh, where is it?
I don't know.
Oh,
There.
there's a blank page in between.
Yeah,
That's
like
weird.
a problem.
Oh, this is such a good problem, too. I know, it's so good. There's a concept in here that's super important. So I'm so glad you realized that we hadn't done this problem. Okay, so we've got a cone. And when we're talking about a cone, we're talking about, the funny cone.
The knot cone.
The knot cone.
The hourglass.
The hourglass cone. So we have a point that's not on the cone. Double check, because if it was on the cone, what would the distance be? 0. So we want to find the points on the cone nearest this point. So double check that it's not on the cone. 1 plus, yeah, that doesn't match. Okay, so it's definitely not on the cone. So we've got some point not on the cone. And we want to figure out the point or points on the cone that are closest to that red point. There's our point P. So what we're going to do is define the distance between the point and the cone. The distance would be the square root of x minus 1 squared plus y minus 4 squared plus z minus 0 squared. So that's our function. That's a function we want to minimize, so we would have to do the second partials test on that. There's a big square root. We'd have to partially differentiate that and then partially differentiate it again. Sounds terrible. But what we can do is square both sides, and here's the concept that I was alluding to that's super important. Do you agree that, let's call this function just something easier to manage like w. Do you agree that function d and function w will have the same critical points?
Yes.
Do you agree that the point that minimizes the distance would be the point that minimizes the distance squared? So if you have 2 points, you can calculate their distances, 2 points, you can calculate the distance between them, you can calculate the distance squared between them. And the distance squared function will have the same critical points as the function d.
How far can we push that? Like, should you do like the distance to the 5th power, or is there a limit somewhere? Like, let's say you had like some 5th root or something. Could you take both sides to the 5th power? Or does it still work?
It's a little different when we have, if we possibly have. That is what you're saying is true if we're dealing with all positive stuff.
Oh,
know,
for
there's
like
just the fact
for
that
odd powers, it wouldn't always work.
Yeah, for odd powers, we'd have to be a little bit more careful. But the idea is, the important thing is that if you have a function that's, and actually it may work even with odd powers now that I think about it. The idea is that as long as your function is increasing, if your function is increasing, if you pick 2 points down here, if this has a bigger function value than that does, then the square of this is going to be bigger than the square of this.
Right.
And if you have an increasing function, and you take 2 points down here, if that's less than that, then the square of that is less than the square of that.
It might be weird if like one was positive, one was negative, or something.
Yeah, if one,
Like
yeah,
less
dealing
than
with
one.
negatives, we might have to be a little bit cautious, but
Less than 1 or something.
but when we're dealing with distance, we're always dealing with positive numbers anyway. So okay, so that's going to be a little bit easier to take partials and second partials of. Way easier. So let's just multiply this out. We get x squared minus 2x plus 1 plus y squared minus 8y plus 16 plus the z squared. So let's figure out w, let's call it w, it's a little easier. W sub x is going to be 2x minus 2. W sub y is going to be 2y minus 8. W sub z, 2z. So those are our first partials.
Why is it x squared minus 2x? Oh, never mind. That's negative.
Did I write it correctly?
I wrote it wrong.
Oh, good.
Yeah.
I prefer that.
Oh, good.
I prefer you wrote it wrong than I wrote it wrong. Because then all you guys have to erase. Now only Grant has to erase.
If only I used
Poor Grant.
pencils.
If only.
If it weren't for my crippling graphite allergy, not addiction.
Whoa! Will you quit chewing on graphite? Freaking me out. Okay, so W. Wait, what am I? Hold on, now I'm confused here. Distance formula. Hold on. What am I thinking? Hold on, 1 second. I lost my train of thought here. So we have our surface. We have our function that we want to minimize. And we are going to, what are we going to do? We're taking our partial derivatives. Oh, let's find critical points. I started doing these things before I found critical points. Sorry. So critical points. We have to set them each equal to 0. So we find 0 equals 2x minus 2. So that tells us that x is equal to 1. Critical points. So the distance or the distance squared function is going to be minimized or maximized at a critical point. So we're going to find the critical points. Critical points are where the first partials are simultaneously 0 or where 1 is undefined. We don't have that situation here. So we get this guy, and then we set that equal to 0.
Nice arrow.
Yeah, nice arrow. Nice arrow.
It's going the wrong direction.
Let's start over. Start over.
Amazing.
Your hands moved a little too fast.
Too fast for the board. Slow down.
It's the same as the point.
Yeah.
That
Is
doesn't
that
make
just a
sense.
coincidence?
No, something's wrong. So that cannot be right. Oh, duh. What am I doing? I'm taking the partials of the wrong curve. Right? We've got we're trying to,
Oh my God.
the function, we're trying to find points on the cone. Right? We're trying to find points on the cone. So the distance function, we're trying to figure out critical points on the cone. We're trying to find points on the cone. So we should be partially differentiating our cone, not the distance formula.
So why'd we do the distance?
So the distance formula is going to be used, but not quite yet.
Killing this boy.
Not quite yet.
Not quite.
Sorry about that.
Sorry about that. Sorry about that.
Right? Do you agree that the critical points are on the cone? Because it's points on the cone that are going to be minimizing and maximizing distance.
So we're trying to look for the points on the
So
cone
erase
that are
everything
closest
we
to
just
that.
said.
Yes, the points on the cone that are closest to that point. So we should be partially differentiating the cone, right?
Okay, so.
So hold on,
X.
yeah,
I'm
let's-
not in the mood to erase all that.
Yeah, I think you need coffee right quick during the break.
This water's not doing it.
Yeah.
You need that bean water.
Let me just look at that for a
Maybe put a little
second.
straw.
Bean water.
Bean water.
Coffee.
So yeah, so we just differentiated and
Did
found
you
the
drink
point
all your
that
bean
we
water?
already had. So that's not helpful.
Oh, yeah.
So the distance from there to there, distance. So when we partially differentiate our cone, I gotta think for a second though, because when we partially differentiate that, you gotta think about the concept. Because the function we're minimizing is the distance function. It's the distance function that's subject to the cone. So we should be plugging values into, let me just think for 1 second here. So let's look at the last problem. So the last problem, we were minimizing or maximizing a function on the boundary. So we, let's get back to this problem in a minute. All of a sudden I'm getting confused. Because if we take the partial derivatives of the cone, if we're taking the partial derivatives of the, it's the function that we're trying to minimize is the distance function. Right? It's the distance function that we're trying to take, that we're trying to minimize or maximize. Would there be a maximum?
No.
No, because the cone goes up forever, so there's going to be no maximum. So the critical values for that distance function are going to correspond to mins automatically because there's definitely no maxes. So when we take our partial derivatives, it does feel like we should be taking them of the distance formula though, because we are minimizing that.
Well, because if you took them from the cone formula, would you have to take the square root of both sides to
Yeah,
get C?
exactly. So
Okay.
that's why I'm looking at that and thinking.
'Cause that'd be super
it
hard.
seems. So we are.
Won't
Let
be
me
that
just-
hard.
Let's go. Let's start. Let me
One
just.
half
Oh, we'll come back to
differentiate,
this right
right?
after the break, unless someone has an idea.
Would this possibly be one of the cases where squaring the distance function does not?
No, that always works. That definitely always works. And we do have to partially and because that's the function we're minimizing, it does make sense that we have to partially differentiate that. But maybe
Maybe that is right.
maybe if the is that a critical value?
1 plus 16 does not equal
Well, I'm
0.
Yeah. Let's start the next section and I'll look at it during the break and I'll figure it out. There's an easy thing I'm missing there.
What's the important thing that you wanted to tell us that was the purpose of it?
That you could minimize distance squared and minimize distance. That minimizing distance squared is easier than minimizing distance. And that's why I'm thinking, yeah, you do have to take those partial derivatives of this because I know that we go to distance squared because that's a pain to partially differentiate. So we do have to partially differentiate the distance squared formula.
Why don't we try differentiating the one where it's not squared and see what happens?
No, you can do that. You can do that. There's some simple step here that I conceptually I'm not seeing at the moment. I'll figure it out during the break.
Would you say anything?
During the break, we will do it. All right, so let's go to our last section in this chapter, the Lagrange multipliers. And the Lagrange multipliers actually is a technique, using a Lagrange multiplier is a technique to do what we're trying to do with that distance problem. It gives you another way to calculate the max or min of a function relative to a constraint curve.
You sure that slide didn't just get put in the wrong file?
Yeah, I'm positive. There's another, we can do it with the other way. There's some little nuance I'm spacing out. Okay, so our goal is to find the max and min values of a function subject to a constraint. So this is very similar to that roller coaster one we looked at, where we've got a paraboloid and we've got a curve in the xy plane, and that curve projects up onto the surface. So we've got this ellipse up on the surface, and we can clearly see that there's a max and we can clearly see there's a min. And we could get at it using the techniques from 12.7, but here's how we're going to do it with 12.9 with Lagrange multipliers. So what we have to do is observe the following. The idea is that the level curves for the paraboloid are here in green, and then our constraint curve is in blue. That's the curve down in the xy plane, that circle of radius 2, diameter 4. And notice that when you're thinking about maxes or mins based on this constraint curve, you can imagine drawing lots and lots of level curves, and at some point you're going to get a level curve that's going to be tangential to your constraint curve. So the level curves are curves of constant function value. So as we're moving out with these concentric green circles, the value of the function is getting bigger. So if we're looking for a max, you know, I don't know which constraint curve, the level curves, he doesn't say which ones they are. But as we're moving further and further out on these curves, we're getting larger and larger function values. So here, where the constraint curve passes this level curve, whatever that level curve is, that's what the function value is there. But we know that that function value is bigger because we're at a level curve that's further out. And we know that that function value is even bigger because we're even further out. So the idea conceptually is that you can draw all these level curves, and then the one that's tangential to your point is going to be the one that's creating the maximum. Because the next level curve out is not even going to touch your constraint curve. So that level curve right there is corresponding to the max. Similarly, if we went for the mins, we can see the min value is going to be over here corresponding to that point. It's probably supposed to be right on the axis. Or maybe not. So we start looking for mins, and it looks like it's going to be right there, right? That's the innermost level curve that corresponds to a tangential point. So that's going to correspond to a low point according to this constraint, because this level curve has lower function values than this one has. So we're always going to conceptually be able to do that. You're going to be able to draw your level curves to a point where it's tangential to a max or a min. And so what that means is that the gradient of our function, so the gradient of our surface, that's going to be perpendicular to its level curves. So the gradient is going to be perpendicular to all the green stuff. So del F. Del F is going to be perpendicular to every level curve. And at this particular point of tangency, isn't the normal vector to that constraint curve also perpendicular to the corresponding level curve? So the idea is going to be if we can find the places where del F is parallel to the normal for that curve, that's where the maxes and mins will occur. The places where the maxes and mins occur will be where we have the normal to the curve and the gradient to the level curve where they're parallel. So this is normal to the constraint, to the blue curve. And so the normal to the constraint being parallel with the gradient, that'll correspond to these points that we call Lagrange critical points. And that will find the max and min subject to a constraint. So we'll try it out. So here is a picture, kind of like the one we looked at on Wednesday with the roller coaster curve. So the constraint, we have our surface. Again, it's a paraboloid opening upward. And the constraint curve is down here in the xy plane. It's this red ellipse. That's a constraint curve. If you project it up onto the surface, you see this roller coaster curve. And when we compare it to the level curves, the green curves are the level curves, we're trying to figure out where the level curves have a point of tangency with the constraint curve. And those are the 4 places. And so it's just an observation again that the low points, there are the 2 low points, there are the 2 high points. Those are going to correspond to places down in the domain, in the xy plane, where the normal to the constraint curve is parallel to the gradient of the surface. Gradient always lives down in the xy plane. The gradient of a surface is down in the xy plane. The normal to this curve is in the xy plane. And so where those 2 are parallel will correspond to Lagrange critical points. So let's see if we can find such things. So here's our surface. The gradient to our surface, that's a vector valued function. That will be y squared comma 2xy. Now let's get a normal to this curve over here. The normal to a curve the way we've been doing it is to create a parent function and take its gradient. So the parent function for the constraint, we could build this function g of xy equals x squared plus y squared. We know we don't need to deal with the constant because we're about to partially differentiate. So del g 2x comma 2y, that is normal to the constraint curve. So this is normal to constraint. It's normal to this constraint curve right there. All right, so now we have a vector normal to the curve. We have a vector normal to the level curves. Now we want them to be parallel, which means one is a multiple of the other. So the formula that we usually use is del f equals lambda del g. So lambda is the Lagrange multiplier. Lambda is Greek letter L for Lagrange. So this tells us that that vector del f is parallel to del g. Question?
No, I'm just nervous.
Yeah, you should. You're just nervous. So if we want to set up this system of equations, y squared will equal 2 lambda x. You can draw a lambda. It's not too hard. And then 2xy, don't be nervous, equals 2 lambda y. Now, we have three unknowns. We've got x, we've got y, we've got lambda, so we need one more equation. Anyone know what the third equation will be?
The constraint.
The constraint. The constraint will be the last equation. So now we have three equations and three unknowns, and we can calculate, we can find our Lagrange critical points. Yeah?
Okay, so when you set up your y squared equals 2 lambda x, did you just, what is that formula? Del f equals lambda del g?
Yep.
So you're just sort of like dotting it, or you're?
This is a scalar.
You're setting it
Lambda is a
equal.
scalar.
Okay.
So when we multiply a vector by a scalar, the scalar jumps into each component.
And it's 2 because there's a 2 over here.
Which two? That
y
2?
squared equals 2 lambda x.
Yeah, that 2 is this 2.
You're
That's
just setting components equal. to
Setting
each other.
components equal. So we're going to set that component into lambda times that component.
Is lambda just a
Lambda is a real number.
So if it was
just
3.
a variable basically?
It's a it's a variable. It's
Okay.
unknown, but it's going to be a constant.
Okay.
It's going to be a numerical variable. And we often don't find lambda. We're curious about x and y. We're looking for ordered pairs, x comma y. So sometimes you may solve for lambda, sometimes you won't. If you get your ordered pairs without solving for lambda, that's fine. You don't often need lambda. Sometimes it'll be easier to find lambda first, but not always. So we look at this thing now, and we've got to solve this system. So this is a nonlinear system. We've got to figure out how to solve it. So what we're going to do is look at let's see, what are we going to do? What are we going to do now? So let's go ahead and look at this second equation first, because what I notice is that I have a common factor of 2 and I have a common factor of not W. Y. So xy minus lambda y equals 0. So I'm going to divide out the 2 and put everything on the left so that we can factor out the y. So this tells us that we have that, and this tells us that y is 0 or x is equal to lambda. Those are our two possible solutions.
So you just need 2 equations to solve this?
So we have 3 unknowns.
Yeah, but you just need 2 equations.
So often we just use 2 of them and then we'll use 2 but then plug into the third. So right now we have 2 possibilities here, and when y is 0, we're going to have one thing going on. We're going to have 2 cases that we have to work out. Okay, so let's consider the case where y equals 0 is not that interesting, but let's write it down first. So when y equals 0, let's put it over on the side. So when y equals 0, we have the when y is 0, we're going to plug that in down here. So when y is 0, what does x have to be? So x has to be plus or minus 1. Get that? And then when when x equals lambda, that's going to be a more interesting case. So when x is lambda, we can figure out, maybe in this case it might be beneficial to solve for lambda. It doesn't always matter. But what we can do is look at the combination with the first equation. So we can replace that lambda with an x, because lambda is equal to x, and so then we're going to get an xy equation there, so we can get a relationship between x and y. So plugging into the first equation, so we get y squared equals 2x squared. You follow that? So we plug that into the first equation. So this right here, lambda and x are equal, so we're going to plug in right there. That gives us a relationship between y and x. Then we can plug that into the constraint equation so that we can solve for one of the letters. So if we plug in y squared equals 2x squared, so into constraint, that's going to give us 3x squared equals 1. So x squared will be 1/3, and x will be plus or minus root 3 over 3 if we rationalize. So that creates two possible x values. We then have to find the corresponding y values. Let's move this thing down. We need some more space. So let's create a list over here of Lagrange critical points. So I'll call them Lagrange critical points. So x is going to be positive root 3 over 3 or negative root 3 over 3. And then what is the corresponding y going to be? So to find the corresponding y's, we know that x squared is 1/3. So we're going to subtract that over. So y squared is going to be 2/3. So that tells us that y is going to be plus or minus the square root of that. So it looks like the square root of 6 over 3. So we're going to have this one with a positive square root of 6 over 3. This one with a positive square root of 6 over 3. And then the next one down will have negative square root of 6 over 3. So we'll have two more points here. So we're going to have positive square root of 3 over 3 with a negative root 6 over 3. Negative root 3 square root of 3 over 3 with a negative root 6 over 3. So we've got those 4 points. All right, so questions up to that moment? Will?
Yeah, so pretty much, yeah, for the stuff you have over on the right, are you just arbitrarily picking equations from those list of 3 you have there?
Yeah. So this equation only has 2 in it, right? 2 letters. So if we can eliminate lambda from up here and then plug into there, then that gives us an equation with 1 variable that we can then solve and then back substitute into that. So we basically eliminated lambda from the top 2. And then with this one over here, question?
Yeah, so is the point of the Lagrange multiplier to simplify this process?
Yeah.
I think you could still do it without lambda, right? You could solve for one variable, plug it in, get some equation, and...
Yeah, we didn't find lambda, though.
Well, right, but what I'm saying is we introduced lambda to the system of equations. Could you still do this without lambda?
No.
Why not? Couldn't you just solve for y? Then
Because we need to figure, because lambda is the multiplier that guarantees that these two are parallel. So we can't say that they're equal, but we can say that one is a multiple of the other. So, and we don't necessarily need to find lambda, but lambda is going to be part of it because del f is not equal to del g, it's a multiple of del g. So we're scaling del g to get del f. And then how about the x equals plus or minus 1? What's y going to be? 0. When x is plus or minus 1, y will be 0. So that's going to give us 1, 0, and negative 1, 0.
You have y equals 0 on the top.
Say that again?
Yeah, you have y equals 0 on the top, so you don't need to find y again. You get y equals 0.
Oh yeah. And so now that's going to correspond to x equals 1 and x equals negative 1. So we just have to make sure we get them all. So those, yeah. So we already knew y was 0. Yes. Thank you.
I need a peanut.
All right. So Are there any other critical points?
Join me.
Nope, we took care of everything. We had two possible cases. Y equals 0 led to x equals plus or minus 1. X equals lambda back into the first equation led to those ones. So we have 4 Lagrange critical points.
6.
6. 6.
Math.
6, math.
You missed parentheses on one of them.
I did?
Yeah.
Right there. Thank you. And now we just test them. Figure out the max and the min. Throw them into the function.
After breaks.
Function. We're going to plug them into the function, then we'll take a break. F is equal to xy squared. That's easy. All right, so plug them into the function. So x times y squared, we're going to have 6 over 9 times this. So that's 2 root 3 over 9. Somebody be checking this arithmetic. Plug in that one, and I think we're going to get the same thing except negative. Are we agreeing with that value? No or yes? 6/9.
Nobody can do it as fast as you.
6/9, 2/3, 2, okay.
Please stop.
All right.
Please
All right. Please stop. Please stop. All right. This one is going to be 2 root 3 over 9 again. This one is going to be negative 2 root 3 over 9. This one is going to be 0. This one's going to be 0.
Well, you did it 4 times, right?
4 times.
So
I must be
you
right.
either got it right.
I either
the
got it
whole
right or got it
time
wrong.
Got it wrong. Yeah.
So what is the absolute max?
Definitely those two.
Definitely that. So that's our absolute max. And then our absolute min, right there.
Values are correct. Yeah.
Okay, great.
So those are our absolute maxes and absolute mins. And this is where they occur. So we have the location and the values.
So those two at the bottom don't.
So these two just don't, they're Lagrange critical points, but they don't correspond to maxes or mins. Yep. All right, let's take a break. Take a break, take a break. And let's resume. Okay. How many variables is the distance function? If we're finding the distance between 2 points in 3-dimensional space there, how many variables do we want this to be a function of?
3, 2, 1.
We would, when we're taking partial derivatives, wouldn't it be great if we only had 2 variables?
That would be awesome.
Yes.
Yes!
You're finally right. Yes. So what do? How do we make it a function of 2 variables?
See that Z?
Yes.
Get the eraser and...
Yes. And what should we put in for it?
0.
What is true? So we said that somehow we have to incorporate the cone into it, right? We have this distance formula that's just the distance between any 2 points. This right now we have the distance formula between that point and any point in the universe, but we want it to be between that point and the cone. So what do we have to do? Plug in the cone. Somehow this distance formula, right now it's between that point and any point in the universe. We want it to be between that point and this cone. So somehow we have to plug the cone into there.
Plug it in for z squared.
Plug it in for z squared.
Bada bing, bada boom.
Bada bing, bada boom. Yes, so that's what we do. So we'll erase this stuff. Yes. So that, yeah. So we do want to be partially differentiating the distance formula because that's what we're trying to minimize or maximize. But we have to somehow incorporate the object that we're finding the distance to. Somehow. It's got to be included, right? Duh. So we are going to just rewrite the distance squared formula with our z squared, and z squared is x squared plus y squared. Plus x squared plus y squared. So we are now finding the distance between the point and the cone. Duh. Somehow we have to include the cone. Does that make sense?
Yes.
All right, the distance formula, we can write out the distance formula, but this is the distance formula to any ordered triple, x, y, z. So to force it to be the ordered triple that goes to the cone, we have to replace one of the letters with the cone equation. And so we're going to go with z squared. Replace that one. That's the easiest. You could replace the x or the y and then have different partials and it would still work out. But we're going to replace the z squared with what it's equal to. So then w sub x looks a little different than what we had before, but not too crazy. So we're going to get 2x minus 2 plus 2x. 4x minus 2. The y's, we're going to get 2y minus 8 plus 2y. So 4y minus 8. 4y minus 8. Now we set those equal to 0. 4x minus 2 equals 0. We get x equals a half. Set the second one equal to 0. And we get y is equal to 2. So that is those are the x and y coordinates of these points, of the point or points. Now we have to find the z value. So z squared is equal to x squared plus y squared. So let's set up our little table. We're going to have x, we're going to have y, and when we plug in to that equation right there, what do we get for z? We get 1/4 plus 4, which is going to be 17/4. And then we take the square root of that, so we're going to get plus the square root of 17 over 2. And our second point will have the same x and y, but minus square root of 17 over 2. So those will be our 2 points. These are the points that we're looking for. Yes. Yes. Must include the cone in the distance equation.
So there's 2 points?
2 points.
Mm-hmm.
There are 2 points because if you think about our cones, Calc 3 cones look like that. So there's one on top and one on bottom. Yeah. Mm-hmm. All right, so that we did it that was one way to do it. With Lagrange multipliers, you can also do it. You could do this with Lagrange multipliers treating the cone equation as your constraint. So we could find the gradient of that, the gradient of our distance squared, set them equal to each other. And that's how you pull the cone in, by taking its gradient and then setting del f equal to lambda del g. That would also work. We will do another distance one with the Lagrange multiplier very shortly. Okay, so let's go ahead and do this other Lagrange multiplier problem. Let's get a new page. We don't have enough space. Let's cut, add, paste. Okay. All right, so here's another one. We have a surface, a function, and this constraint is a curve in the xy plane. Let's figure out the gradient of our surface. So gradient of f, del f, is going to be the vector 1 comma negative 1. Again, the gradient lives in the domain. It's down in the xy plane. It's not up on the surface. And then over here, we have a constraint curve. We need a normal to that constraint curve. So what we're going to do is build a parent function that has the constraint curve as a level curve. The gradient of our parent function will be normal to the constraint curve. That's the normal to the constraint curve, del g. And then we're going to do del f equals lambda del g. This is the equation that guarantees the parallelness of the two vectors. The parallelness. This is a parallel exercise. All right. So now, do you agree that we could put lambda on either side? When I look at this, it's like, well, wouldn't it be easier to multiply lambda by del f? It doesn't really matter. When you say two vectors are parallel to each other, it's just one equals a constant multiple of the other. So we could do it either way. This looks a little easier because del F is so simple. Right, so
Can we
let's
do
it.
that?
Yeah, let's do it that way. So we're going to do 2x minus 3y equals lambda times 1. And we're going to do 2y minus 3x equals lambda times minus 1. And then we have to put our constraint curve here also. X squared plus y squared was, what was it? Minus 3xy equals 20. All right, so those are our 3 equations. 3 equations, 3 unknowns. We may or may not need to solve for lambda. Most of the time, you can just eliminate lambda and not deal with it. What happens if we add these 2 equations together? Doesn't that just eliminate lambda? So if we add those 2, lambda goes away, and we end up with minus x minus y equals 0, or in other words, y equals negative x. And that can then be plugged into the constraint equation, which only has 2 letters in it. There's no lambda in it. So then we're down to 1 letter. 1 letter is good. So we're going to have x squared plus x squared minus 3x times negative x equals 20. So our constraint equation is how we are going to solve for one of the variables. And that gives us,
That's so nice.
doesn't that give us like x squared equals 4?
Yay.
That's not too bad. So x is plus or minus 2. So we have, what do we have then? So if we go back up here, we
How'd you get
have,
4?
Yeah.
pardon?
You should get 10, not
You have
4.
x
Oh, did I
Yeah.
multiply wrong?
No, because you have
plus
5.
4x squared. You should get 6x squared.
No, you have 5x squared.
5. I still see 5x squared.
Yeah,
Oh, yeah, you
5x
should-
squared equals
5.
20, and then
Yeah,
you divide
sorry.
both sides by
Yeah.
5.
Okay, so that looks right.
Wait a minute.
Oh,
Yeah, 2 plus 3 is 5.
2 plus 3 is 2 plus 3 is 5.
20.
Oh man, we are really reinforcing the
Does that
arithmetic
20
tables
play a
here.
role in anything?
So
We
the
had to
20?
divide-
Yeah.
Oh, well, we divided both sides by 5.
Oh, okay.
So the 20 is important because we divided by 5. Okay, so when x is 2, what's y equal to? Yep, so these are our Lagrange critical points. When x is positive 2, y is negative 2. When x is negative 2, y is positive 2. So those are the only 2 Lagrange critical points.
What did you
And-
plug that into, sorry?
We plugged right back into that. So we combined our first 2 equations to get an xy relationship
Into the original.
into the original combined equation.
That's
right.
It's just getting more and more fun.
The original combined equation. This is our, right, when you do a simultaneous solve, you have 2 equations and 2 unknowns. You plug one equation into the other equation, you get x equals whatever, and then you plug back into the first equation. So this is acting like our first equation in the xy system. We eliminated lambda to create an xy system. So this is our first equation in the xy system. This is our second equation in the xy system. So plug one into the other and then back substitute.
And your 2x squared came from that relation, right? The y equals negative x, so x squared plus x squared instead of x squared plus y squared?
Mm-hmm.
And it's not negative because you squared it?
Right,
Okay,
exactly.
okay.
So it's x squared, we plug the y, we replace that with negative x squaring, gets rid of the minus.
Okay.
Yep. Mhm. So we have 2 critical points, Lagrange critical points. They're not critical points for the surface, but they're critical points for the subject to the constraint. So now we go back to the function, we figure out our function value, and we get our Lagrange max and our Lagrange min. So we do x minus y minus y is 4, negative 2 minus 2 is negative 4. So this is our Lagrange max, our constrained max, and there's our constrained min.
These are absolute max.
No, not absolute, because absolute is for the function itself, for the surface itself. So this is subject to this curve in the xy plane. So we have some circle or ellipse in the xy plane, and then we've got this tilted plane up there, and we're sort of dealing with the high point and a low point of that tilted ellipse on that plane. So they don't call it an absolute, they call it a constrained max or a constrained min.
So just to make sure I'm not going crazy, when we when we do the
You're asking a lot, Grant.
The del. All right. When we do the del f equals lambda del g, or
Yep.
the del g equals lambda del f, we're setting ourselves up to have one of two completely different lambda values there, right?
Yes.
It's okay.
One,
So,
I mean, they're related. They're reciprocals of each other.
okay.
Right.
But
they're
not
and
the
they're
same.
both constants, but they would be different.
Okay.
Yep, that's right.
My second question is, could you call those absolute constrained maximums or absolute constrained minimums? Because what if there were more than one max within that constraint?
Yeah, I mean, you could kind of say that. That's possible because you could have multiple, sort of local constrained maxes, right? And then one that's the absolute of those. I mean, usually they just say a constrained max or min.
Okay.
But that idea is possible. You could have something that's undulating up and down, and you could have one that's higher than the others, but you could have local ones in the middle. Yep. Okay. All right. I don't think we skipped a slide. You guys ready to try one? You look so ready. Ready, set, go! Go! You're not ready? If you're not ready, we can do another one together. Should we do one more first?
Yeah.
All right.
Yeah.
We'll do one more then. We'll do one more. I'll just write that you tell me what to write. Del f is equal to
If he was not ready, then nobody's ready.
y plus 1. Good.
X plus 1.
Excellent. That is really good.
Excellent.
Excellent. And then del g.
2x.
No.
I'm sitting here.
2x plus 1.
Oh, you're talking to yourself, not
I'm
me.
talking to myself. Sorry, I.
So
that's
what about
just-
del g?
That's using that other one, right?
Yep. So our g is built off of this guy. We can ignore the constant and just say del g is that,
Okay.
or g is that. So del g is
2xy squared.
2xy squared, comma.
X squared y. 2x squared y.
Yeah. Very good.
They have to go in alphabetical order.
Do you want to put lambda in front of del f or lambda in front of del g?
Del f.
Del f, okay. So we're gonna, it doesn't matter which one we do, we could do it in front of either. So our three equations will be those two by setting them parallel, and then our constraint is our third. All right. So perhaps we want to eliminate lambda from the first two equations. We could just divide by the x plus 1 and the y plus 1 and then set them equal. See what happens? Let's do that. Get rid of lambda. Or another thing we could do, there's lots of things you can do. One thing we could do is try to match the left-hand sides. We could multiply the top row by x, so we have a 2x squared y squared. Multiply the second row by y, so we'd have a 2x squared y squared. So then we'd have equality that way. That would also work.
Wouldn't you just subtract them and get rid of lambda?
Well, if we
No,
subtract,
that wouldn't
because
work.
there's a
That's-
one with an
yeah.
x and one with a y. So we
That's
can't
how it works.
quite do that. But we could multiply top by x, bottom by y, or we could divide both. What do you want to do? Doesn't matter.
Multiply by x.
Multiply by x. Done. So the top equation will become 2x squared y squared equals lambda x times y plus 1. The second equation multiplied by y gives us 2x squared y squared equals lambda y times x plus 1. So we get that. Make sure that's a y. This is getting close. They're looking similar. So we have that. So now we can set those two equal to each other. So all we did was multiply that one by x. Let's see, multiply by x. This one we multiplied by y. So now we subtract the two, or whatever we want, however we want to think about it. Set them equal to each other, if you will. Don't the lambdas just divide out if we set them equal to each other?
Yeah, they do.
Yeah, they do. So we get that.
How do they cancel?
The lambdas are numbers. So we have a number here and a number here, so we can just say, hey, let's divide by lambda.
But how did you get there? Did you did you subtract off the left?
I just set them equal to each other. So if 2x squared y squared is equal to that, I can put that right there.
So
Oh,
Right?
okay.
Right? So we have two different expressions for the same expression, so those two different ones can be set equal. Does that make sense? If you have x equals a and y, if you have x equals a and x equals b, then a and b are the same.
Should I be getting x equals y?
Let's find out. That sounds like, that's what this kind of looks like. So when we multiply this out, we get xy plus x equals xy plus y. So it looks like x has to be y. I agree. So now we have two xy equations. So the top two equations boil down to one xy equation, and then the constraint curve is always an xy equation. So now we have two equations with x and y. So now we plug one into the other. So we're going to have x equals y, so we're going to have 2x to the fourth equals 4. So we're going to plug that in right over here.
Where's the 2
why'd you
coming
get
from?
2? Isn't it just
Because I added
a random
some
number?
random,
So
randomly added.
the fourth root of
I
4?
added, say that again?
So just the fourth root of 4?
4 through to 4.
Or
So
1.4?
X equals, well, let's do it this way. Let's not do it that way. Let's first, it's always better to factor when possible. So do you agree that this would be the factorization? Don't want to lose anything. We do that. Because we have to have 4 solutions, 2 of which are going to be real. So this guy contributes no real solution, so we could ignore it. But the other one will contribute to 2 real solutions, plus or minus the square root of 2. And that tells us that our Lagrange critical points, don't make fun of the French. So we have x is equal to plus or minus root 2. And we go back to the first xy equation. So we plug the first xy equation into the second. We got some x values. We go back to the first. So it looks like we have these 2 critical points, Lagrange critical points.
And yeah, we get those based on x equals y, right?
Yes.
Why did we cross out x squared plus 2?
Because if that were set to 0, you would get x squared equals negative 2, which has no solution.
Okay.
Because you
Ignore
can't
that.
take the square root of it.
You can't, not if you're looking for reals.
No.
Not if you're trying to be real.
If you're trying to be real.
But
you're trying to
you're an
be fake.
imaginary. So xy plus x plus y. Wait, I did not write that correctly, did I?
Yes.
xy plus x plus y. Okay, one extra factor of x gone. Okay, so then we just plug and chug into this to figure out the values. What do we get? 2 plus 2 root 2. And then we get 2 minus 2 root 2. And what?
I just said, what are we even trying to do here?
Find the max and min!
Oh.
Find
I
the max
forgot about
and min.
that.
Find the max and min. So we get those 2 values.
Sorry.
The one, so okay, so we have those 2. There's one question I want to ask you. And that is, let's see, there's one question I want to ask you, and that is at which step is it? Not there. Oh, it's there's one step I want to ask you, and that's right here. So we canceled out lambda, but what is true when you cancel out on both sides? Are you always allowed to divide out?
assuming that it's
You were assuming that it's
Positive. No.
positive or
Yes,
not zero.
Well, yeah.
We're assuming that it's not zero. So right here, we did make one little assumption. So we had to assume that lambda was not zero if we want to divide both sides by a number. You're assuming that it's not zero. So we do have one secondary case. What if lambda was zero? If lambda is zero, does that add any extra Lagrange critical points?
0 equals 0.
So if lambda is zero, then we would have, let's write it down over here. So if lambda equals 0, we get 2x squared y equals 0. And that would imply that x or y equals 0. Okay. So if lambda is 0, then you're forced to conclude that either x or y is 0, if lambda is 0. So if lambda is 0, that means x or y is equal to 0. And if x or y is equal to 0, does that add any extra critical points? If you plug in x equals 0 here, does it give us anything else?
0 equals 4.
Yeah, so it doesn't give us any extra critical points. But it is a case that we have to be careful with. We cancel that out. That means we divided both sides. Yeah, that can only happen if what we're dividing is non-zero. So we should just double check that when it is equal to 0, that we're not missing any extra critical points.
So if x squared y squared was equal to 0, we would have missed a critical point?
So if, let's suppose this was x squared y squared plus x plus y equals 4. So if somehow this didn't just boil down to something that was inconsistent, then we might get another x value or another y value. So if this was, it's even simpler. If this was x plus y equals 4, if x is 0, then y would be 4, and if y was 0, x would be 4. So we'd get a couple of extra points.
Where x is 4 and where y is 4.
Yeah, yeah, we get extra points. But here, 0 equals 4 doesn't matter, so we don't get any extra points. Okay, so this is going to correspond to our max, and that's going to be our min. Max and min.
Does Lagrange work with 3 dimensions?
Yes,
4 dimensions and all forms of
Mhm.
dimensions?
we will do one shortly. 3 dimensions, yes. Yeah, you can keep on doing it. All right. Oh,
Think of a double.
there you go. There you go. That's what you were waiting for.
Sure, that's what it is.
Okay, so let's write down del f. Del f, pretty straightforward there. We're going to have a yz for the first component. For the second component, we have an xz. For the third component, we have an xy. And then del g, write it right below it, seems easier. Del g looks like 2x, comma 4y, comma 8z. Can you see that without writing out g is equal to? Set g equal to just the left side sufficient. You can ignore the constant. And then we write del f equals lambda del g, so we're going to create a big system here. So we're going to have yz is equal to 2 lambda x, and then we're going to have xz is equal to 4 lambda y, and then we're going to have xy is equal to 8 lambda z, and then we're going to have the constraint, x squared plus 2y squared plus 4z squared equals 9. All right, so now we've got to somehow mash those all together and plug into the constraint and find an x, y, and a z. All right, so if you look at this, you can combine the top two equations in a way to possibly eliminate one letter. Let's see, let's look carefully. If we could go through a multiplication thing. If we multiply this by y and multiply that by x, that would get us, so we could get rid of lambda that way and get a relationship between x. Oh, well, we're still going to have 3 letters though, right? So we're going to have to somehow, I think what we want to do, if we can use the constraint equation, if we can write y in terms of x somehow, if we can, you know.
Why don't you just solve for lambda in the first two?
Okay, we could do that also. We could do that. Let's try that. That's a great idea. I mean, there's quite a few ways that we can go. So let's put 2 lambda on the right-hand side for both of these. So we have y z over x is going to equal 2 lambda. And then the other, so that is the top equation. The second equation is going to be xz divided by 2y. So we have xz divided by 2y equals 2 lambda. Does that look good? That's one possibility. What I'm noticing right now is that we could also, well, we'll get, it doesn't matter. There's so many ways to go. So we set those equal to each other. So we get yz over x equals xz over 2y. So we'll have to be a little careful because we just made an assumption. We'll get back to that assumption. We just assumed x is not 0. We assumed y was not 0. So we have those assumptions in our back burner. So we have this. So we end up with 2y squared z equals x squared z. So this tells us that we have, if we subtract, we get z multiplied by 2y squared minus x squared equals 0. Perfect.
Let me just take the, never mind.
Divide by z thing.
Yeah.
So you can divide by z, but then you're introducing a secondary if z equals 0, so we have that. Yeah?
If I take the first equation and divide by the second one, I get 2y squared equal x squared.
You said this equation divided by this equation? Or this divided by this?
No, the left one.
These two?
Yeah.
Yep.
And I got 2y squared minus x squared equals 0.
Yep.
Which is,
Same as that.
yeah.
Yeah.
It's shorter.
Yeah, yeah. So it's not always obvious what's going to be the shortest way, but that's what Hung just said is absolutely true. You could divide the first equation by the second equation. Definitely. There's a lot of ways you can go. You can combine the first and the third equation. There's lots of different ways. We'll all get the same thing in the end. So we have that. So x squared equals 2y squared. So that is going to allow us to plug into the constraint equation. So x squared, that can get replaced with 2y squared. So now we know what our goal is. Now our next goal is to replace the z with y's somehow. Yeah?
And I use the second one divided by the third one.
Yeah.
It's not the same.
Yeah.
Plug it in.
Yeah. Should we try that? So we'll do it a little differently for the z's. So if we divide, so let's do, so the way you did it then, what you're essentially doing, we have to be a little careful when we're dividing. So are you saying that you're dividing this by this and this by this? Let me just think about the logic of that. If we have A equals B, let's just check and see if that's a possibility. So the question is, are we allowed to say this? Can we say that? And this is then going to say that AD is equal to CB or BC, whatever. So I have to think about that. There might be a little bit of a problem with that.
But
I know it worked in the first case, but
for the last line is A is equal B, right? D and C equal, so they should be equal. You have A in the left side, B in the right side.
Yeah,
A is
yeah,
B,
yeah,
so
yeah.
B
You
has
introduce
C.
the assumption
yeah, that's right. So you if you multiply this side by A and this side by B, those are equal. So yeah, so division will also work. You're right. That will work. You're right. That will definitely work. All right, so let's try it then. So we're going to divide this one by this one. So we're going to do.
I don't think division will work.
You don't think it'll work?
No.
What if
We're
C
going
or
to
D
introduce the
equals zero?
assumptions to
That, well, it creates extra assumptions for sure.
Yeah.
That
It
we would.
assumes that you can't have z equals 0.
Yeah, so then we'd have to have a separate case, which
Okay.
we will have to analyze anyway because we already have z equals 0
Zero,
there. So let's try it. I've never done this before. So 2 divided by 3, we're going to end up with z over y. And we're going to end up with lambdas go away, y over 2z. Over 2z. So we get 2z squared equals y squared. So we can then plug that in. All right, so let's go for it. So in our constraint equation, we are going to have, we have x squared is being replaced with 2y squared. And then we still have 2y squared. And then 4z squared. Multiply both sides of this by 2. So we get another 2y squared equals 9. So then we're going to end up with y squared equals 6 divided by 9, which is 3/2. So y will equal, I feel like we already had this critical point earlier.
Wait.
It's 2/3.
Did I multiply wrong?
Yeah, you.
Did you say 6 divided by 9?
Root 3.
6 divided by 9 is 9 over 6, which is 3 over 2.
Okay.
Root 3 over 2.
So root 3,
Wait,
so that's going
wait.
to be root 6 over 2. Oh, I think that's right. So we have 6y squared, 9 divided by 6 is 3/2, square root is 3 over square root of 2, rationalize, we get square root of 6 over 2, plus or
Oh,
minus.
you rationalized.
Rationalized.
Yeah, okay.
So
Didn't do that.
now we have two y values. That will correspond to two z values here. That will correspond to two x values over there. And we'll consider the 0 thing in a minute, because we assumed z wasn't 0. We assumed y wasn't 0. We'll consider those in a minute. All right. Get this. This thing probably has to go to another page. All right. So let's get all of our ordered triples. So we have. Let's build a table, I guess. So y is going to be root 6 over 2. Y is going to be minus root 6 over 2. When y is root 6 over 2, let's go for the x's first, over here. It's probably easier to look at y squared. Y squared is 3/2, so x squared is going to be equal to, now we're going to have, I'm going to do it this way. I need more space here, so let's go like this. Let's try to minimize our, so we're going to have square root of 6 over 2 for y, and when we plug that in over there, we said that we're going to get plus or minus root 3. So we're going to get root 3, we're going to get minus root 3 for the root 6 over 2. And then for the negative root 6 over 2, we're also going to get two values. And the two values are going to be the same, right? We're going to get root 3 and negative root 3. Okay, so we've got all that.
Don't you need,
Go ahead.
don't you need 4 of the root 6 over 2s? Because if you put the z's in, you have 2 z's as well.
Yeah, so we're going to probably have to have more. Yes, yes, I think you are 100% right. So now we go to the z's, and the z's are right there, so we're plugging in our y squared is equal to 3 over 2. Divide, we get 3/4, we take the square root, we're going to get plus or minus root 3 over 2, I think. So plugging in 3/2 there, we divide by 2, so we have 3/4, we take the square root, so we get that. So yeah, we're going to get a plus or minus. We can put a plus or minus at least for one of these maybe, and we'll see if it works. Okay, so that was plugging in the y squared into there.
Wait, why did you?
What's it going to?
Say again.
What's it going to?
So we're plugging in this
Yeah.
y squared right there,
Yeah,
getting two z's. We plug in this one right there. We're also going to get, see, do we need 2 for that one also? Yeah, we need 2 for that one also, right? Do you agree? Right? Because the y, we have y equals positive root 6 over 2. With this one, that's going to correspond to two different z values. We have the positive root 6 over 2 with that one. That's going to correspond to 2. So we're going to have 2 there, and then the same is going to be here. We're going to have plus or minus root 3 over 2. So yeah, we have a ton of points. Ton of points. So we get all those. Okay, now let's consider the zeros. So what happens when z is 0? So up here, where was our z equals 0? Let's go to that one first. So when z is 0, come over here. When z is 0, we are going to get that these two sides are 0. So let's write it over here. So z equals 0 if z is equal to 0. The top two equations, or look at this third equation. If this third equation, all of them have to be true simultaneously. So if z is 0, what's true about x and y?
X or Y should be 0.
One of them has to be 0. So if z is 0, then x or y equals 0. Now they both, can we get to a point where they simultaneously all have to be 0? That would be great. Right now, we said if z is 0, one of x or y is 0. So if z is 0 and y is 0, that would give us x values with y 0 and x 0, or y 0 and z 0, and vice versa. So we want, it'd be ideal if we can show that if one is 0, all are 0, because if all are 0, we get no more solutions.
Yellow looks like
So-
for the top two equations, yeah, you get x must equal 0 for the top one and y must equal 0 for the second one.
So if we go up to the top one, so we know x or y is 0, so let's assume that x is 0. So we know z is 0, and we know x is 0. Well, if z is 0 and x is 0, does that force y to be 0 in one of these equations?
I don't think they ever can all be simultaneously 0, because your constraint 0 plus 0 plus 0 equals 9.
Well, that would mean that there's not an extra Lagrange critical point.
Right, so I don't think they could all be 0.
Well, they can't all be 0 to make a true critical point, but if these three equations force x, if z is 0 and that forces both x and y to be 0 up here, that would tell us that that point can be excluded, that there's no more critical points.
Because that point
But
doesn't
if they
exist.
are, then
But
us
if two of
assuming
them
0
don't imply the
wrong.
third being 0, then we could have a whole bunch more critical points, where x is 0 and y is 0 and z is plus or minus this.
And then like us
Yes.
assuming
So
those
let's
things
hope,
was wrong.
let's hope, let's hope. Okay, so if z and x are 0, does that force y to be 0? z 0 and x 0 do not force y to be 0 there. Right? If z is 0 and x is 0, do not force. If x and z are 0 here, does that force y to be 0?
Yeah.
It forces y to be 0 as long as lambda is not 0.
Oh my gosh.
Right? Do you agree? Now, if lambda is 0, then we're in a whole bunch. Okay, so now this says that lambda or y is equal to 0. So if we go up to the top one, we have x equals 0, y equals 0, and then either lambda or y is 0 from the previous one. So to me, it looks like we're not going to have any extra critical points because there's not going to be, I think all three have to simultaneously be 0
Well,
if one is 0.
Because if x, if you take that second one.
Mm-hmm.
Oh wait, never mind. Nope, that's exactly what you just said.
But let's just go on. So let's just say that no extra critical points. Let's analyze these million that we have. Okay, so now we have to go to the function and analyze them. So the function is just the product of them all. So this point here, the function is the product of them all. So we just multiply them all together. And what do we get? So we're going to get a plus or a minus here because we have one point that's alternating signs. So let's see. So we get 6. No, what am I saying? 6. Root 3 times root 3 is 3. So we get 3 root 6 over 4 plus or minus. 3 root 6 over 4. Everyone agree with that? We multiply those together. The 3 pops out. This one, what do we get when we multiply them all together? Same thing.
But Nick,
So positive, so if we choose the positive root 3, we're going to get a negative, but if we choose the negative root 3 over 2, we get a positive.
can you still just put
But it's
plus or minus?
still going to be plus or minus 3 root 6 over 4. And looks like it's going to be the same all the way down, right?
Zero.
Right? So this tells us that our max is positive 3 root 6 over 4, and our min is going to be minus 3 root 6 over 4. So that'll be our max and our min.
And those just occur at multiple places.
And they occur at lots of places. Yeah.
Mhm.
So it's like that roller coaster thing where you could have lots of high points and lots of low points. So it is what it is, yeah. All right.
Can we do one more in 15 minutes?
Let's do another one. Let's put this one on another slide there, just to make sure it's cut.
So I'm supposed to finish this one today.
All right. Let's try one more of these suckers. Del F. This part's the easy part. We like this part. Solving the system that's hard. Okay, so del G. We're gonna have to be a little more clever over here because we have 3 components now. So G, we either have to subtract the variables to the left or subtract the Z to the right. And it doesn't matter. It'll all come out in the wash. So our del G is going to be minus 4xy. G sub y is going to be minus 4. Oh, there's supposed to be a square there.
Square, yeah.
Yep. Minus 4x squared y. And our del, or our partial with respect to z is 1. All right, so that will generate our system. So we are going to have, I think it's going to be easier to put the lambda with the f. So we'll do 2 lambda x. And then we'll have minus 4x squared y equals 2 lambda y. And then we're going to have 1, let's see, we said that equals lambda times minus 1. And then we have our constraint. Z equals x squared y squared plus 1.
2x.
2x squared y squared plus 1.
I vote third equation.
I love the third equation. Okay, so here is one where it looks like solving for lambda makes a lot of sense. So lambda must equal -1. So let's figure out what that means with the other equation. So if lambda is -1, this tells us that 4xy squared equals 2x if we multiply both sides by -1. And it tells us that 4x squared y equals 2y. So this is from plugging the lambda into these and then multiplying by -1. Okay, so now we have to simultaneously solve those. I think multiplying the top equation by x makes sense. Bottom equation by y. So we'd have 4x squared y squared equals 2x squared. And we have 4x squared y squared equals 2y squared. That tells us that x squared is equal to y squared.
Why can't we just divide x out of the top one and y out of the
Because
bottom one?
then
You
you
can.
would come out with assumptions that you
And
have to
then we just have to
evaluate.
check if x is 0, if y is 0. Yep.
So it would
When possible, it's best not to divide by a variable.
Because
If
then you
can,
don't have to check
if you can
those
avoid it.
assumptions.
if we multiply, we don't need to check 0, right?
Say that again, Hung?
So if I divide the first one by the second one, I need to check 0.
Yes.
And if not,
Yes. And so down here we have that this is going to tell us that x is equal to plus or minus y, or y is equal to plus or minus x.
If you're multiplying the top by x and you're multiplying the bottom by y, could we just always assume x equals y? Because that's happened in the last 2.
Say that again. Can you assume that x is equal to y?
When you multiply the top,
Top
by
by
x and
x.
the bottom by y,
Yep.
the last 2 times always come out as x equals y, or x equals plus or minus y.
I don't think that's always true, but that's a good question.
Okay.
I gotta think about
Because
that.
wouldn't it be just x times something is equal to y times something?
But the equations aren't equal, though. Part of the equations are equal, but not. I gotta think about that. That's a good question, because we have come up with the same.
Right.
There might be something there, but I don't feel like that's a general principle. We'll find out. We'll study. Okay, so now we have that x squared is equal to y squared. So if we plug that in down here, we have to get down to this constraint equation. So z is going to equal, if we plug in y squared, we're going to get 2y to the x squared is getting replaced with the y squared, so we get 2y to the 4th plus 1 equals 0. Oh, whoops, not equals 0. They're just equal to each other. All right. Now the z is in no other equation, right?
Nope.
No other equation. So,
Is it a free variable?
well, this is telling us that, yeah, the z is not in the other equation at all. When we partially differentiate, it goes away. Huh, interesting. Okay, well, let's just see where this goes. So we've got a relationship between x and y. We've put it in here. So this feels like z is going to be free. Or it's going to depend on y. Because we cannot eliminate z.
Do you
Well, then
have
the
to
same thing would have been the same if you plugged in
If we
y
went,
for x and
if we,
flipped it around.
yeah, then I'm not
X for Y.
sure.
Does this mean we should get everything in terms of z then?
But we can't get.
Because that's the only one you
have y
can
there.
get in terms
You
of
could
z.
solve for y in terms of z, plug z back in, try to solve. Oh, but you'd never be able to get x in terms of z.
Yeah, if we take the constraint equation and we solve for y squared and put it up in here,
We'd still
solve
have
for
z.
x squared and put it up in there,
We'd still have like a random z.
I don't see how we can eliminate all the variables.
What if we,
Let's look at this conceptually for a second to see if there's something weird.
What if we divided x out of the first equation on both sides, and since we know that lambda is equal to -1, then we can solve using that. It would just leave us with x, and it would just.
Does it
leave
give us
with y.
numbers?
It does
Yeah.
give you numbers if you do that, but then if you have to do the assumption where
Right.
One
And that
is
might be
equal
what we
0.
have to do then, because right here, if we cancel out the x, oh, that's definitely what we should be doing. Because when we plug in there, we end up with a roadblock. We can't solve for a number. We have z and x, we don't have, or z and y, we don't have another equation. We can't do anything. Right here is where we should jump out and get numbers, right there. Because that allows us, this leads to a dead end right here. Because when we go to our constraint equation, we have two variables we can't get rid of. So this leads to a dead end. This leads to a dead end. No, you're absolutely right. This is the spot right here. We can solve right there. That we can put, and instead of, we can either divide it, or we can just subtract it and factor it and say x is 0 or. It doesn't matter. Both of those do the same thing. So if we divide it out, we get this. And then this is with the assumption that x is not equal to 0, so then we have to just go back and double check that assumption. And so that, yeah, that's where we want to go.
The assumption kind of kills it though, because you can't properly define the other variable if you assume that one of them is equal to 0.
So,
And then that doesn't work in the last.
well, we'll see. Let's get there. Let's just do this first, because we have to get numbers, and we can't get numbers the other way. So this way's got to work. It's just a question of how it plays out. We'll get there. So we get plus or minus root 2 over 2 for y. And if y is plus or minus root 2 over 2, we're going to come right back up to here to get x's. Where are we going to get our x's? So can we get x's from this right here? So we're going to go to this equation right up here to get x's, the second equation. So from the first equation, we get our y's. From the second equation, we're going to get our x's. And we're not actually necessarily plugging them in, because this equation does not depend on y. We can cancel out the y in the same way. So we have 4x squared equals 2, so x squared equals 1/2. So x is also going to be plus or minus root 2 over 2. So the equations are independent. We're getting x values from one, we're getting y values from the other, and then the z values we'll check down here from the constraint equation. So this tells us that when y is root 2 over 2, x can be either. When y is negative root 2 over 2, x can be either. Like they're independent of each other. Right? As long as y is not 0, y is not 0.
And x is not 0.
And x is not 0. So let's plug those in to get our z. So our z will equal,
1/4
let's,
times
yeah,
2, so 1/2.
so we can look at let's imagine first that that's our y value.
Well, can we just use the y squared
Yes. So y squared is a half, x squared is 1/2, so we get 1/4 times 2 is 1/2, so we're going to get z equals 3/2 in every single case. Do you agree? Right? If we plug in y squared in here, we plug in x squared, it doesn't matter if we choose the positive or the negative, because we're squaring, we're going to get 3/2 for every single case. So we're going to have the following points then. We're going to have x equals root 2 over 2, with y being root 2 over 2 or negative root 2 over 2.
Yes, pretty much plus minus root 2 over 2, plus minus root 2 over 2, 3 over 2.
Yes, exactly. That, we just write them all out. We would have that, 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 that.
It's like once you get one thing, then it all just.
And it all unravels.
So you're gonna put one of these on the exam and that's it?
Yeah, exactly. One is all we can take.
Jesus.
All right, so then
This is
these can be
unreal.
long. So what is it? X squared plus y squared minus z. X squared plus y squared minus z. X squared plus y squared minus z equals f. Yeah, one of these is plenty. We'll do one on the test that has 2 variables, not 3.
Okay.
Definitely.
So don't practice 3 variables.
Definitely 2
Not
variables,
for
not
the
3.
Not for the exam.
All right, so then we square each of these things, and we already know that y squared is a half and x squared is a half, so we're going to get 1.
That's what we're
So
doing.
don't we get negative 1/2?
Yeah.
And I believe we're going to get negative 1/2 all the way down. Is that right? Okay, so then let's analyze the weird case. So the thing that we did, we divided out the x, so we assumed x was not 0, we assumed y was not 0. So now we just say to ourselves, what if? So if x is 0 or y is 0, what's true about z?
Z has to be.
So if x is 0 or y is 0, then z is 1. So if x is 0 or y is 0, then z has to be 1. And when we look at our thing here, if x is 0 or y, it's right over there. So we have to just figure out the function value. So what about when x is 0? What does y have to be? Does it predict y? When we know x is 0, do we predict y?
Well, assuming lambda isn't 0.
So if x is 0 here, y could be anything. If x is 0 here, y could be anything. So y is some arbitrary constant. Let's just put it there as a c. Same type of thing happens with x. So then the function says that we're going to add x squared plus y squared minus z. And are we going to get a specific value, or is it going to go up and down forever? So if we have 0, we're adding x squared plus y squared minus 1. So doesn't this sort of go up forever? Do you agree? If c is a constant, so if c can be any y value, this can be as big as we want, and so this is going to go towards plus infinity. And similarly, this is going to go towards plus infinity, not minus infinity though, right? Do you agree? It can't go towards minus infinity? Because that's squared, so we can't go towards minus infinity. So what we have is a min but no max. So our min value is minus 1/2, but we don't have a max value. And we have no max value. Because the values keep getting bigger and bigger. No min, so we have a min but no max.
So if you had divided by x and you just subtracted, would you have to do that?
Well, when you subtract the x, you still have the thing where you factor out the x, so then it says x is 0 or x is whatever the other thing is. Yes, you have to deal with it both ways. It's just a lot easier when there's 2 variables. So I think what Haley said is very important.
What did I say?
You said that
Oh.
if the 3 variable ones are so complicated that they're not on the exam, we should focus on the 2 variable ones. which is probably a good thing.
Just for the exam.
Just for the
Like,
exam.
We'll do the other ones.
Do the other ones for fun.
For
Right.
Do the other
homework,
ones.
not for fun. For
Oh, okay,
homework.
homework.
Is that gonna be similar with the absolute
Fun.
min and max?